Good morning, everyone. It's great to see so many people out here in person. So welcome back to DARPA In-Person Summit. On behalf of the Department of Energy, I do want to thank our DARPA hosts for inviting us to participate in this really exciting event. As you just heard, my name is Andy Schwartz. I'm the Division Director for the Material Sciences and Engineering Division in the Office of Basic Energy Sciences at DOE. The DOE missions in energy, science and security, and science and innovation and national security are both enabled by and support advanced computing and microelectronics. Given the importance of microelectronics across DOE, last year the department stood up a working group with representation from across the agency. The group is charged with ensuring efficient coordination and information exchange within the department, as well as with our interagency partners. I'm here today representing this whole working group. DOE stresses the importance of investing in a broad range of semiconductor technologies, including the innovative power and analog electronics needed to support our nation's clean energy, electrification, and grid modernization goals. The department also stresses the importance of investing in trusted and assured supply chains of radiation-hardened microelectronics, radiation testing, and advanced packaging capabilities. Sandia National Labs Microsystems Engineering, Science, and Applications Facility, or MESA, produces laboratory, custom-designed, industry-produced devices accredited by the Trusted Foundry Program. In addition, it actively keeps tabs on commercially available state-of-the-art microelectronics devices globally through the Electronic Parts Program, is currently conducting a risk analysis on commercially available parts required to produce nuclear deterrence systems. DOE's National Nuclear Security Administration, or NNSA, provides space-based sensor systems for the United States Nuclear Detonation Detection System. Current designs incorporate both Sandia Mesa and commercial device technology, heterogeneously integrated by an industry partner. Advanced sensor system concepts under consideration will introduce both quantum and cryogenic technology to the suite of capabilities. The current U.S. government plan to have quantum networking components in space per NASA-sponsored roadmap and necessary qubits will need cryogenic cooling. DOE investments in microelectronics to support advanced computational needs, such as high-performance computing, are critical to support modeling and data analysis used across DOE's mission space, from the design of clean energy technologies to the simulation of nuclear weapons to the advancement of foundational science. Primarily through the Advanced Scientific Computing Research Program, or OSCAR, DOE has a long history of innovations to advance energy-efficient, high-performance computing. The combination of fundamental research, test beds, and industry partnerships to deploy leading-edge machines is essential for feeding the innovation pipeline for DOE's use cases and the broader CHIPS programs. Earlier this year, DOE marked the dawn of the Exascale era with the announcement that the Frontier supercomputer at Oak Ridge National Lab had achieved 1.1 exaflops of performance. This ranked it #1 in the world in performance, and equally importantly, Frontier ranks second in the world in energy efficiency based on the Green 500 list. Frontier's performance and efficiency were enabled by public-private R&D partnerships in the Exascale Computing Path Forward program and previous programs spanning more than a decade. Underlying these incredible advances in computing capabilities are years of foundational research into materials, chemistries, devices, and fabrication processes. In 2018, the DOE Office of Science organized a workshop entitled Basic Research Needs for Microelectronics, which laid out a set of priority research directions for fundamental research needed to enable next-generation microelectronic technologies. In recent years, led by the Office of Basic Energy Sciences, my home office, DOE has dramatically expanded investments in fundamental science for microelectronics through programs such as the Energy Frontier Research Centers and a group of DOE lab-led co-design R&D projects. In addition, Basic Energy Sciences operates 12 open-access user facilities that enable scientists from academia, national labs, and industry to carry out research that cannot be done at their home institutions. These facilities include X-ray light sources, neutron scattering facilities, and nanoscale science research centers, some of which are shown on the bottom of this slide. The Advanced Research Projects Agency, Energy, or ARPA-E, aims to enhance the economic and security of the nation through investments in disruptive technologies. Investments in electronic materials, devices, modules, and circuits provide the knowledge and capabilities to increase energy efficiency, reduce greenhouse gas emissions, and improve the resilience, reliability, and security of our energy infrastructure. ARPA-E has invested more than $300 million in over 75 semiconductor-related projects, with tech-to-market activities integrated into each one to support the commercialization transition from lab to market. With computing and communication technologies requiring increasing fractions of global electricity, a focus on energy efficiency is critical. That is why the DOE Advanced Materials and Manufacturing Technologies Office, or AMTO for short, has launched the Microelectronics Energy Efficiency Scaling for 2 Decades initiative, known as EASE-2. To date, 57 separate organizations have signed the EASE-2 pledge, committing to work toward these goals. The initiative is intended to provide an RD&D roadmap for technologies needed to continually reduce microelectronics energy use, a new energy efficiency scaling law for microelectronics. This EASE-2 initiative effort kicked off with a series of AMTO-sponsored workshops that included strong interagency collaboration with participants from OSTP, NSF, DOD, NIST, as well as industry and academia. AMTO now has formed 7 working groups to formulate different aspects of this roadmap, from materials and devices to advanced packaging and heterogeneous integration to metrology and benchmarking. Looking ahead to the CHIPS R&D investments, we at DOE think DOE, and particularly the DOE National Labs, can contribute significantly to both the National Semiconductor Technology Center, the DoD Microelectronics Commons, and other CHIPS R&D programs that we've heard about this morning. DOE has a long history of working with U.S. industry to accelerate advances in microelectronics R&D, manufacturing processes, and product development. Maintaining U.S. superiority in post-war innovation will increasingly require DOE's unique capabilities to realize next-generation devices, which will likely feature both decreasing length scales and increasing materials and fabrication complexity. Some of the distinctive capabilities available at the DOE National Labs include discovery, fabrication, and processing of new materials, X-ray and neutron characterization across length and time scales, sub-angstrom imaging capabilities, exascale computing, as I mentioned earlier, and testing under extreme conditions. As an example, the DOE labs have worked closely with industry over many years to advance the extreme ultraviolet technologies critical to producing today's leading-edge chips. Much of this work began in 1997 as a partnership between Intel and 3 DOE labs, Lawrence Livermore, Lawrence Berkeley, and Sandia, and it continues today with an emphasis through the Center for X-ray Optics at Lawrence Berkeley National Laboratory. But as you all know, well, there's so much more to do, and many challenges are beyond the reach of any one agency. DOE and our labs are committed to contributing to the whole-of-government approach envisioned by the CHIPS and Science Act. Which is why DOE has included funding in the fiscal year 2024 President's budget request to launch the Microelectronics Science Research Centers that were authorized in the CHIPS and Science Act. If funded, these centers would be a $300 million investment over 5 years, building upon ongoing foundational microelectronics research supported by DOE. Each funded at up to $25 million per year, the centers would focus on fundamental science and early-stage research, complementing the later-stage RD&D investments already being made through CHIPS, including the NSTC and Microelectronics Commons. These centers would leverage the broad and deep infrastructure and expertise at the DOE labs that I've already spoken about. And these centers would support multidisciplinary teams, bringing together the DOE labs with academia and private industry to ensure broad geographic and institutional representation, including minority-serving and emerging research institutions. The success and impact of such centers will depend critically on their integration into the broader semiconductor R&D ecosystem, which is why the type of interagency coordination and cooperation reflected here today is so critical. On behalf of all of my DOE colleagues, thank you for your attention. Enjoy the rest of the meeting.